Today, we're going to talk about a brilliant engineering method that is, well, it's literally all around you, holding up our modern world. It's this technique that let us build the massive, complex structures that define our cities, and they did it all without a single computer. So, to really get a grip on the problem they were facing, let's just look at two different engineering challenges. Over on the left, you've got a simple beam. Calculating the forces on this, pretty straightforward. Engineers call this statically determinate. But look at the one on the right. With all those extra supports, every single part of the beam affects every other part. The math just becomes this tangled nightmare. This is a statically indeterminate problem, and for the longest time, it was pretty much impossible to solve with any real accuracy. So that's the big question, right? How on earth did engineers in the early 20th century tackle these unbelievably complex structures? They didn't have computers to run all the numbers. So how did they manage to design the skyscrapers and sprawling bridges that completely defined a new age of architecture? This challenge, what you could call the unsolvable bridge, it forced a complete rethink. This wasn't about trying to find a bigger calculator. It was about finding a totally new, almost philosophical way to understand how forces naturally find their own balance. And the answer? It came from an American engineer named Hardy Cross. He came up with a solution that, wasn't based on these impossibly complex formulas. Instead, it was built on a simple, kind of elegant idea that systems in nature always want to find balance. As he put it, equity in distribution is a natural law. He called his technique the moment distribution method. Now, instead of trying to solve for everything all at once, which was the impossible part, his method treats a complex structure more like a living system that wants to find its own equilibrium, just one little step at a time. Okay, to really understand this, let's forget about bridges for just a second. I want you to imagine a group of people, and they're all standing around a big, rigid, interconnected table. Their job is to balance a heavy, really awkwardly shaped weight that's been put on top. No single person can do it alone. They have to work together, constantly adjusting and readjusting until the whole system is perfectly stable. That table analogy, that's the whole key. The entire method, as complex as it sounds, can really be broken down into three core concepts that those people around the table would totally understand just by intuition. First up, we've got stiffness. In engineering, it's just a beam's resistance to bending, but in our analogy, it's even simpler. It's just how strong each person is. The bodybuilder at the table has a really high stiffness. Maybe a toddler who wandered in has a very, very low one. Next is something called the distribution factor. This is basically the rule that decides how any imbalance gets shared. If the table suddenly tilts, who takes the most strain? Well, the distribution factor says that load gets shared proportionally. The strongest people, the ones with the highest stiffness, they take on the biggest share of the work to get the table balanced again. Makes sense, right? And finally, there's the carryover moment. This is the ripple effect. Because that table is rigid, when one person pushes up to make a little adjustment, a part of that force actually travels through the table and affects their immediate neighbor. And then that person has to adjust too. It's a chain reaction. So with just those three simple ideas, stiffness, distribution, and carryover, we can now see the absolute genius of Hardy Cross's method in action. The method itself is this really beautiful, repeatable process. First, you pretend all the joints are locked tight, and you figure out the initial forces. Then you go to just one joint, you unlock it, and you let it balance out. Those forces get distributed to its neighbors, and that carryover effect ripples through. Then you lock it back up, move to the next joint, and you just do it again. You keep cycling through all the joints, balancing and rebalancing. Now, have a look at this table. And seriously, don't get bogged down in the math. That's not the point. Just watch the pattern. See what happens with each new row? The initial forces, they're pretty big, but with every single cycle of distributing and carrying over, the adjustments you have to make get smaller and smaller and smaller until they're basically zero. The system literally converges on the final stable answer. It balances itself out. So the really crucial point here is that this iterative process, it wasn't just some clever math trick. It was a complete game changer. It unlocked a whole new world of design possibilities for engineers. And this slide really shows why it mattered so much. I mean, this was a pre-computer superpower. For the very first time, engineers could confidently design these incredibly complex, indeterminate structures. This method gave them an almost intuitive feel for how forces would flow and balance out. And here's the kicker. The core logic of this method, iteratively solving a problem until it all settles down, is the fundamental basis for the powerful structural analysis software that every engineer uses today. This leaves us with a really fascinating thought. The moment distribution method showed us that even a problem that seems completely unsolvable, like a complex bridge, can be understood just by patiently balancing it piece by piece. So it makes you wonder, what other complex systems in our world, whether it's in economics or ecology or even in our own lives, could we understand a lot better if we just applied that same patient, iterative search for equilibrium?